students. So today we want to talk about derivatives, and I'm sure now you are very good with limits and also continuity. But today let's look at how do we end up defining derivatives, still using the idea of limits and continuity that we have learned previously. But before, let's start with the tangents. In fact, we'll start with tangent lines. So suppose somebody gives you a graph of the form, and then we call the graph C. So let's say on this graph you have some straight line which crosses this graph twice. So it crosses this graph twice at a point P and at a point Q. So this line that crosses our curve twice, we'll call it second line. So that will be called the second line. And one thing which you can realize is that suppose Q approaches P, that means the point Q gets closer and closer to P but still on the curve C. You may end up with a line that touches the graph once. So this is still a straight line that touches the graph once. So let's assume that it touches the graph once at a point P. So this will be our tangent line. That's one thing to bear in mind now. We have two lines that are of importance here. You have a curve C, and then on a curve C we can define a new line, straight line, which crosses the curve C twice. We can also define another straight line called a tangent line, but which crosses the curve once at a point. It touches the point once. So this is what we are saying. If a curve C has an equation of the form, and we want to find the tangent line to C at a point A, f of A, then we may start somewhere in the neighborhood. That means we may start first by computing the slope of the tangent of the second line. Remember the second line before. So that will mean if it's your second line here, and then if we want to give this point here, we can define this point at P to be A, f of A, and then at Q you can define it to be x, f of x. Then the slope to that is y2 minus y1 divided by x2 minus x1. So which is nothing but this part, which is the slope of the second line. But what did we see from the second line? We have seen that as Q approaches P, actually the second line approaches the tangent line. So the second line approaches the tangent line. So as Q approaches P, we can see the limit of the second line now becomes the tangent line. Or in other words, to make Q approach P, we can just let x to approach A. That's what we'll see. As x approaches A, definitely Q will approach P. What are we talking about? Where are we going? We want to start from the second line and then use the knowledge of the second line to move to a tangent line. So suppose again you have your second line here which goes through the point P and Q, and then P is still defined by A, f of A, Q is defined by x, f of x. So you can see that the distance between x and A can be defined by assuming that x is bigger than a can be divided by x minus a, or the value of the difference between the two is just x minus a. And also, if you look at the vertical difference, it's just f of a minus f of x minus f of a, whichever is bigger. But here we assume that f of x is bigger than f of a, to be on the safe side. So, let's look at the graph on the right to see what we said previously. We said suppose you start with your second line here, and then assuming that this point is nothing but x, and then the point P is nothing but a. If you let the point Q to get closer to P, we said you can do that by letting x to get closer to a. So let's take a value of x that is closer to a. Now if you move a little bit towards a with x, you can see Q is getting closer to P. You move again to the next value of x, which is closer to a. You can see Q is moving closer to P. Finally, we end up landing on this line, the red line, which we call it a tangent line. So we can see that defining a second line with 2 points P and Q, and as Q moves closer to P, the second line approaches the tangent line. So we can say the tangent line is the limiting position of the second line as Q approaches P. That's what we can conclude from here. That's what we can conclude from here. The definition of the tangent line. Remember, we said the tangent line is the limiting position. It's the limiting position of the second line as Q approaches P. And remember, we said to make Q approaches P is the same as saying let X approaches A. So we can say the tangent line is defined to be the tangent line to the curve at a point P, which is a comma f of a, is the line through P where we have the limiting of the second line as Q approaches P. That means as X approaches A, provided that this limit exists. So this will be the slope of the tangent line. It's nothing but the slope of the tangent line. So the tangent line slope is defined by looking at the slope of the second line. So what is inside this, what I circled here is the slope of the second line. So we can say it's ms, which is equal to the slope of the second line. So now if we take the slope of the second line and then you let x to approach A, then you get the slope of the tangent line. That's a take home. Think about that. So here is an example. Find an equation of the tangent line to the parabola. This is the famous parabola that we know from our algebra, where you have y and x, and then you have the curve of the parabola to look somehow like that, which has the minimum at 0 here, at 0. Don't mind my bad drawing. So suppose you have the point 1 somewhere here, 1 comma 1, which is 1, and then which is also 1 this side. So this point is P is nothing but 1 comma 1. Suppose you want to find the equation of the tangent line. So let's draw the tangent line to that point. Suppose this straight line touches this point here. And that's our tangent line. That's our tangent line. One thing which you can see from our tangent line and from the behavior of our graph is that the slope is positive. That's one thing to take. And you can see that the tangent line will cross the y-axis in the negative value of the y. So as you solve this problem, have that kind of expectation in your mind so that you can see if you are going wrong. So let's go back to the definition of the tangent line. The definition of the tangent line is that is f the limit as x approaches a. In this case, our a is 1 of f of x minus f of a, which is f of 1, divided by x minus a, which is x minus 1 in this case. And then we can go further and then plug in f of a here, which is nothing but 1. So we have x squared, which is f of x, minus 1 over x minus 1. This is nothing but the difference of two squares. You can factorize to get this, and then you can simplify to get the limit as x goes to 1 of x plus 1 after simplifying. Then now you are ready to substitute. Then you end up with 2, which is what we expected. It's a positive slope. So the slope of our straight line here is nothing but 2. So we need the y-intercept so that we can write our straight line. So this is the slope of the line. Now remember, to get the equation of the line, you need to find the y-intercept, or you can write it in the form of y1 minus y0, which is equal to m, which is the slope, x1 minus x0. Or in general, you can actually leave you can drop the 1s so that you are just left with y minus y0, which is equal to m into x minus x0, so that x and y are stand for any value that you can take. So in that form that we have, we know our y0 is equal to 1, and we also know that our x0 is equal to 1. In this case, where we want to find the tangent line, we want to find it at the point 1, 1. So we end up with a straight line, y, which is equal to 2x minus 1. That's what we got as a straight line, or the tangent line that touches the curve at that point. What are we saying here? We are saying actually the slope of the tangent line to the curve at that point is also the slope of the curve at that point. So this is a slope of two lines. So we are saying that at that point, in this case 1, 1, the slope that you get of the tangent line is the same slope of the curve, but the graphs are different around, but at that point the slope is the same. In fact, what we are saying to see this better, let's try to zoom into the curve, because with the straight line we are clear to see that as we zoom in, the curve will look almost like a straight line. So this is our quadratic curve around 1, 1. You zoom in. As you zoom in, now you are at 0.5. Remember, I started from 0 to 2. Now you're at 0.5 to 1.5. You can see now it's getting closer to a straight line. If you zoom more in, it looks like a straight line, exactly around 1.1. It's not exactly straight line. But what we are saying actually, as we move closer and closer on the parabola y, which is equal to x squared, as you zoom in, somewhere we can approximate the values of the parabola with the straight line. That's where we are saying it looks like a straight line. It's not exactly straight line. So our argument is that the slope at that point, the slope of a straight line is the same slope as the slope of the curve at that point. Only at that point. If you move to the next point, you'll get something else. So what are we saying? The more you zoom, the more the parabola looks like a straight line. In another words, it's very difficult to see between the slope of the parabola and the slope of a straight line. They have the same slope once you get closer. Okay, that's one thing to take home. And this will help you later when you deal with application questions for calculus or derivatives, where this idea will be of great help. Keep it in your mind. Another thing to say is that there is another expression for the slope of the tangent, which makes our life easier, which we like, and which we'll use it throughout, the slope of the tangent. And we'll use it also to divide the derivative. So remember, you had the slope of the secant to be f of x minus f of a over x minus a, and then we say when you take the limit as x goes to a, then this becomes the slope of the tangent line. Now we are saying if you let h to be equal to x minus a, then we can see that x will be a plus h. And if you do the substitution here, and then you'll get the slope of the secant line to be nothing but f of a plus h minus f of a divided by h. That's the thing. And we can represent that on the graph also to say, suppose now you have 2 points, you have a, and then you have two values, you have x values to be a, and then you have another x values to be a plus h, and we can define 2 points. The first point, a comma f of a, or h plus a comma f of a plus h. And that distance between the 2 points, which we used to say is x minus a, now is h. One thing which you can see is that as x gets closer to a, h goes to 0. So in other words, as h goes to 0, here a plus h becomes nothing but closer and closer and closer to a. That's one thing which you can see. And it defines our tangent line from the second line here. That means as a plus h gets closer to a, our second line now goes to the tangent line. That's one thing to take home. So instead of saying as x approaches a, most of the time we will say as h goes to 0. Because as x approaches a, because as x approaches a, h goes to 0. That's what we can see from here. So that means moving from the second line, we can define our tangent line to just say as h goes to 0, then we get the slope of the tangent line from the slope of the second line. That's what we'll use most of the time. So notice that as x approaches a, h goes to 0 because h is defined as x minus a. And so the slope of the tangent line now becomes nothing but this expression. This is a beautiful expression which you would use it for the definition of the derivative, which is the slope of the tangent line. Keep it. It's a very good one. But before, let's look at a little bit of application of the second line, tangent line, by looking at velocities. So, suppose you have an object moving along a straight line according to the equation of motion, which is S, which is equal to f of t, where we can regard f as a displacement given at any time t. We can go back to our expression and then define change in position as f of a plus h minus f of a. and then change in time to be a plus h minus a. So that's what we can look at now, and that can help us to also say, suppose you have an object at a point, at this point at t which is equal to a. That means your object is at a position f of a, and then that object moves to position f of a plus h at a time t which is equal to a plus h. So you can define the displacement of that object to be nothing but f of a minus f of a plus h minus f of t. So that would be the distance s, or the change in distance, which is our displacement in this case. And then that helps us to define average velocity, which would be the displacement, which is the change in distance, divided by time, or the change in time. So we have f of a plus h minus f of a divided by h, which is exactly what we talked about earlier, that we can think of the slope of the second line to be nothing but the average velocity. That's what we can think in our mind, that the slope of the second line, we can interpret it as an average velocity, provided our graph is the graph that defines position of an object at any time, as we see in this case. But we can also be interested to what is called instantaneous velocity, or velocity at an instant. In this case, we are talking about velocity as an instant is nothing but the slope of the tangent line. And here we are looking at a time t which is equal to a. That's the slope of the tangent line. So it defines nothing but the velocity at an instant. That means at a time t which is equal to a. So that's one thing which you should keep in mind as we work on this one. Let's look at one example. Suppose that a ball is dropped from an upper observation deck of CN Tower. I don't know, that building. So some kind of a building, and then you're standing here, you drop the ball, and then the ball goes, suppose this is your ground here. So now they say 450 meters above the ground, so that means your distance from the ground is nothing but 450 meters. So what is the velocity of the ball after 5 seconds? You want to find the velocity of the ball after 5 seconds. You also want to find how fast, that means the velocity of the ball as the ball travels when, or how fast the ball traveling when it hits the ground. So you want to find the velocity right as it hits the ground here. What is the velocity? That's one thing. So for people who are doing physics, they will remember that one of the equations of the motion is nothing but f v0t plus half g t squared, where t is just time. So now we can treat this motion as just a free fall once you drop the ball. So we have our v0 to be 0 here, and then we also know that the gravity can be given by nothing but 9.8, of which it results with the motion of the equation of our motion to be something like f of t, which is equal to 4.9 t squared. We can now find the velocity here. We can now find the velocity at any time t which is equal to a. So at any time t which is equal to a. So we can say our velocity at that instant is nothing but f of a plus h, which we can find f of a plus h here to be a plus h squared, 4.9 times a plus h squared minus, which is this portion, f of a. F of a is the same as that function except that where you have t now you put a squared. You go on, you simplify until you get at this stage where you have 0 over 0, but you factor h out, it cancels, then you end up with 9.8a. So you can see this is the same as 9.8 t. That means you can find velocity at any time now. So we can answer the first question now. The velocity after 5 seconds now is v of 5. Then you get your velocity to be that. Remember, the velocity at any time is defined by 9.8, or you can even say gt, which is nothing but 49 meters per second. So now you want to find again the velocity as the ball hits the ground, but you are given the height. So the first thing is to try to compute the time. You get the time in seconds to be 9.6 seconds, and then you use the time again back to our formula to get the velocity to be 94 meters per second. So this is, now we are trying to think about the slope of the tangent line as the velocity at an instant, or instantaneous velocity. And we want to use that now to define derivative. So we want to use the slope of the tangent line to define the derivative. I hope you got this clearly. We described it, we moved from the second line to the tangent line, then we even went to the application where we can talk about the slope of the second line to be nothing but average velocity, and also think about the slope of the tangent line is nothing but the velocity at an instant. So now let's come back to derivatives. This is what we have already seen, that we have seen this type of limit arising previously, either when you are talking about the slope of the tangent line, or when you are talking about the velocity of an object at an instant. So this will help us to define the derivative of the function. What is the definition of the derivative of a function? The derivative of a function f at a point A, which we can denote by f prime A, or some people can say that's dy dx later. Dy dx is nothing but the slope of the tangent line at a point A. That's why we said the slope of the tangent line at that point is the same as the derivative of the function at that point. So f prime of A is equal to the limit of f of A plus h minus f of A divided by h, as the limit of h goes to 0, provided that the limit exists. We can even do the back substitution and then get back to the previous function that we talked about, that we can make an argument as q goes to p, or instead of saying q goes to p, we can say sx goes to a, then that still define the derivative of the function. But normally we like it in that form. So most of the time you'll see this form, and we'll also call it the finding the derivative from the first principle. So if we hear somebody talking about the first principle, derivative from the first principle, you are still talking about finding the derivative from the definition of the derivative. Example. Suppose someone is giving you a function of the form, and then you're asked to find the derivative at x which is equal to 2 and at x which is equal to a. Straight away the x is equal to 2, remember we have the limit as h goes to 0 of f of a plus h minus f of a divided by a, divided by h. So this is what we said is the derivative at the point a previously. So in this case, our number a is 2. So we equate a to 2, we get f of 2 plus h, and then here we put 2, we get f of 2. Then we still have h, so you plug in these values into the function to get f of 2 plus h, which you get to be 2 plus h squared minus 8 into 2 plus h plus 9. So up to here, that's f of 2 plus h. You also find f of 2. If you plug in 2 wherever there is x into the function, you should get minus 3 as your f of 2. Then you do the simplification that you are good at, and then you end up here where you have the form 0 over 0, meaning that you need to do a little bit of work before the substitution. You can factor the h out, and then you cancel the h, then now you're ready to substitute, and then you get the derivative of the function at x, which is equal to 2, being minus 4. That's good. And be aware that once you plug in the value of h, you no longer have the limit. So some people will still be carrying the limit even after they have substituted the value of h. That will be a problem. We will definitely penalize you for that. So number b, now we are looking at any point a. So straight away we bring the definition, then now we find f of a plus h. Find that f of a is a plus h squared minus 8 into a plus h plus 9. That's from our previous function here. So then you also want f of a minus f of a. F of a is exactly the same, except that wherever you have x, you plug in a. So you end up with a squared minus 8a plus 9. Then you do the simplification again until you get here where you have again the form of 0 over 0 as an indeterminate form. So you manipulate your expression by factoring h out, and then the h cancels. Now you are ready to plug in h. You end up with 2a minus 8. That's the derivative at x, which is equal to a. So that's your derivative. Now, what did we get? We define the tangent line to the curve y, which is equal to that, at a point to be the line that passes through the point P and has the slope m, remember. And we also use this definition to define the derivative by using the slope, that the derivative would be nothing but the slope of this tangent line. That's one thing. In fact, we can even put the equation of the tangent line, which we can say we can write it in the form of m into x minus x0, where our y0 is nothing f of a, x0 is nothing but a, and then the slope is nothing but f prime of a. So this becomes the tangent line, the equation of the tangent line. This becomes the equation of the tangent line in a straight line form, or some people call it point slope form, which is still fine. So whichever way, you can use the point slope form, or you can find the intercept and find the slope separately and then bring back into the equation as you would normally do at high school. All of them are fine. This is the end of the lecture today. Now let's review what we learned. In short, what we learned, we were able to define the derivatives. We were able to find the definition of the derivative. And then we said we can get the definition of derivative by starting from the slope of the second line and then move to the slope of the tangent line. Then we said once we have the slope of the tangent line, we can take that to be the derivative of the function at that point. So there are two things: second line, and then you move to tangent line. So for second line, you need 2 points to define the slope. But for the tangent line, we just need 1 point where the graph touches that function. Then you can find the slope at that point. We even said you can even talk about that as an instantaneous velocity, or velocity at an instant, for those who are doing physics. So that's what we learned today. We learned that given a curve, from the curve, if somebody gives you a point, you can be able to get the slope of the tangent line, and that slope we also said is the same slope as the slope of the curve at that point. Then once we have the slope m, we can be able to get the equation of the tangent line. We went further and then say that slope m is nothing but the derivative of the function, which is what we wanted to define. So, and we used the definition of derivative of a function to calculate derivative of some few functions, to just make an example. So that's what you know today. Go and use that definition of the derivative. Go into the books, the textbooks, and find problems and find some exercises to work out with the definition. Not, I know at this stage some of you know the rules and the laws of finding the derivative, but now we want to just stick with the definition. We'll come back to the rules and the laws of derivative, which makes it easier. But even after you know, or even in the exam, we'll still ask you to use the definition or the first principle to calculate the derivative, even though you know these rules. So you better be very well equipped to handle the definition of the derivative. So this is where we stop. I hope to meet you again next time. Good luck with your work. Let's stop here.